Excuse me. Welcome. I'm going to talk to you about something you probably already know quite a bit about, the electromagnetic spectrum, but I want to review it and contextualize it in terms of what we're studying right now in astronomy, and that is, of course, telescopes. So, telescopes we think of as just being in the visible range, but the great story in astronomy over the last 40, 50 years is the addition of all these non-optical telescopes. That's what I call the telescopes that are used to look for electromagnetic radiation outside of the narrow band that your eye can see. So let's run through electromagnetic radiation basics that, hopefully you've picked up through the years, but if you haven't, let's, do a quick reminder. So it's basically the propagation of energy in the form of electric and magnetic fields. They're created by accelerating charged particles, and they are in return absorbed by moving or displacing or accelerating the receiving charge. So, for instance, visible light that we're looking at, the colors, they all involve a certain narrow energy range of accelerated particles, almost always electrons, and that creates a ripple in the electric and magnetic fields that those charges put out, right? That's how charges communicate with each other. That's why when people say electrons repel other electrons and attract protons, that happens through electromagnetic fields. And if you, just like if you put your hand in the water and you move your hand back and forth, you'll create ripples in the surface of the water. If you have a charged particle, you do that, it creates ripples in the electromagnetic fields around it. So we describe those electromagnetic fields as having wavelengths and frequencies. And here's the whole spectrum. So the narrow band here in the middle is what we usually, only thing that we worry about, right? All the colors stack up in the rainbow because they're stacking up from lower wavelengths to higher wavelength as you go from red to the blue. And then we name the other ends of the spectrum, oftentimes before we even knew they were just a part of this continuous spectrum, right? So the name sometimes makes people think there's something completely different, like an X-ray or a gamma ray. It's got the word ray in there. It seems so different, but really it's just light that is bluer than blue light, right? And microwaves and radio waves, of course, are just redder than red light, right? And so they all have their own sort of fuzzy band that they operate in, and every single one of them is much, much larger than the electromagnetic radiation. If you look at this doesn't even span an order of magnitude in wavelength, right? But super important to us because, we have a biological adaptation to see that stuff. But even like the next closest ones, infrared and ultraviolet, still are larger in spanning many, many more wavelengths than visible light. And so in astronomy, of course, what they have done is they've found ways to capture the electromagnetic radiation in all of these different frequency ranges, and it has really revolutionized our understanding, and I'll show you some pictures at the end of this presentation to show you how much more information we can extract when we look just outside of the visible. So just a refresher, right, as the electric field, the magnetic fields are doing the same thing at right angles, but as the electric field is going up and down, just like any wave, we can describe that in terms of a wavelength. That is the distance in meters from one peak to the next. And that is the primary way that we categorize the electromagnetic spectrum. These are the numbers on the top of this chart here. On the bottom is the other way you can describe them, which is in terms of frequency. Frequency, of course, is the number of times per second that the peak comes by if you're just standing still and the wave comes by you. And those are inversely proportional to you. And really, one is not any better than the other. They're considered interchangeable, especially in astronomy where we're always talking about electromagnetic radiation in empty space. There are some changes that happen in wavelength as you enter in new media like the air or water or glass or something like that. And the Greek letter lambda, I think I already mentioned that, right? The lambda is the abbreviation for the wavelength. And so this is, as you make the wavelength shorter and shorter and shorter, as you go from red to blue light, this is exaggerated for effect, but that's the idea. As you make the wavelength shorter, right, the distance between the peaks is becoming smaller and smaller here, the frequency is clearly going up. And that's what I was saying about how they're kind of interchangeable. Frequency is the one that correlates to energy, though, so a lot of physicists will prefer the frequency designation because higher frequency means higher energy. So as you sweep across this from left to right, yes, the wavelengths are getting shorter, but the frequency is getting much bigger. And the energy required to create or carried by that photon, or that, of course, you absorb when you absorb that photon, is directly proportional to this number here along the bottom. That's why you have to worry in life about ultraviolet X-rays and gamma rays. Every time you absorb one of those, some of that electromagnetic radiation, you are absorbing quite a bit of energy, right? And that causes cellular damage, and that's why we worry about those high-frequency stuff. As opposed to everything that's below red light here, this is less damaging than even visible light, and therefore most people don't worry about these things, right? All of our communications, our Wi-Fi, and our radio waves, and our TV waves, and our cell phone, all that stuff is down here in this low-frequency range. And of course, if you multiply wavelength times frequency, you get the speed of light. And speed of light traditionally denoted by c, right? A very famous, probably the most important constant in science, the 300 million meters per second. And so all of the light travels at that same speed. Doesn't matter what your frequency is, right? As your frequency gets higher, your wavelength just goes down enough to compensate so that you multiply out and get this speed of light. And that's because it's all the same thing. It's the speed that information can travel through electric and magnetic fields. Actually, it's the speed that information can travel through any field. And so actually, it shouldn't even be called the speed of light. It's the speed of propagation for information, right? So gravitational waves travel at this speed. Anything else that you can think of that is massless can travel, is kind of doomed to travel at that speed. Things that actually have mass, like electrons, protons, atoms, and people, we can never attain that speed because we're hampered by the inertia of our mass. Now, one small misconception about this speed of light, right, that comes about from relativity is it is true that all observers will measure the same speed of light, regardless of whether you're traveling towards it, with it, away from it. But the speed of light can change. It does change, depends on the medium, just like any wave. So when electromagnetic radiation hits the Earth's atmosphere, it does have to slow down a little bit. And that's because the nature of the electric and magnetic fields have changed because there's a certain charge density in the atmosphere, right? And it changes again if it has to go through water or glass. The general trend is the higher the charge density in the medium, the slower the electromagnetic radiation gets through there. I think I've already talked about everything on this slide about frequency. Yeah, so when we're looking at the frequency, since that's the energy it's carrying, that's the energy that created it. And so when we start thinking about what we can determine, astronomically speaking, in astrophysics language, when we look at the higher frequency radiation up here on the right-hand side, we're looking at high energy events, right? So in order to create a gamma ray, you have to have a supercharged energetic event happening, and opposed to radio waves. Well, radio waves, that's put out by empty space, right? The cosmic microwave background has the microwave radiation in there, just everywhere in space, and you're giving off, because of your body temperature, infrared, and that's of course the radiation the Earth is also releasing at night that we worry about getting trapped in our atmosphere with the increase of greenhouse gases, right? So everything that has a temperature has atoms in motion, which means you have charges that are accelerating. And so everything, unless it's at absolute 0 degrees Kelvin, which as far as we know, nothing is at absolute 0 in the universe, everything is radiating electromagnetic radiation. It's just a question of whether we are detecting it. So by looking at these different frequency ranges, we're going to find a lot more information because, we won't even see a high energy event if it doesn't happen to emit in the visible range, right? If we're only using optical telescopes. So it really doesn't, you're handcuffing yourself if you can't even look outside of the optical range. And so, of course, this is where a lot of the recent breakthrough astronomy has been happening. I don't know why it ended. I have all these pictures here I want to show you, so let me just bring those up. So here are several pictures taken by different probes that are sensitive to different wavelengths of light. Here's a picture of the sun in the visible range, right? So it's white because it's emitting a broad band of colors. White light is not a specific frequency. White and black are not actually true colors. White is what we call something when our red, green, and blue photoreceptors are all stimulated approximately equally, right? So if you get the entire rainbow beamed in on the same in your eye, then we register that as white. And black is the lack of those colors, right? And so the sun is emitting all of the colors in the rainbow, and so it is actually white when you take it in space. When you look at it through the atmosphere, the blue light gets scattered out, which makes the sky blue. And when you take blue out away from white, you're left with more red, and so the sun appears like orangish or reddish to us as we look at it through the atmosphere. Now, we also have probes out there that can look in X-ray. We'll talk in a different week. We'll talk about the actual technology of how these telescopes actually can capture this electromagnetic radiation. But look at the sun in X-ray. I mean, this is a completely different picture, right? Invisible, it's pretty featureless. And here on the same day, we take a picture of the sun in X-ray, and we can see all these structures and features. And these are related, of course, to solar weather that we talked about so long ago, sunspots and sun flares and solar coronal mass ejections. These things are hard to see. Here's ultraviolet, right? So yeah, even more and different types of structures. You can see some of the currents of plasma as they bubble up to the surface and come back, and the plasma following the magnetic field lines as they circle and come back into the sun. Here's a picture in infrared, right? So you can see the temperature differences where the sunspots are very clearly, even though they weren't visible to the naked eye. So sometimes you get very interesting pictures, are composite images where they'll overlay, right, these false color imaging, right? So that, obviously if you were to actually make a picture out of infrared light, you wouldn't be able to see it. So they have to translate the different frequencies of infrared into colors you can see. And they do this all the time in science, and so that you can actually look at the pictures, and then you can overlay several of these pictures. And some of the most beautiful pictures you've seen of astrophysical objects, right, are actually an overlay of various pictures like in X-ray and UV and visible. Now here's a galaxy. I'm embarrassed to say I don't know which one, but all right, so here's a picture of it in visible light, like taken with Hubble. Right, and so you can see a little bit like we're looking at it sideways here maybe, right? So you can see like a galactic bulge sideways, and then maybe these are like could be some spiral arms, but we can't tell the structure, but since it is pointed sideways to us, but that would be like the plane of the galaxy. Now here's a picture in infrared. Notice that it's quite different, right? So you can see something really interesting, some spherical distribution, a nugget of something giving off infrared light here that was totally obscured the visible light, probably by all the intervening dust and stuff like that. But the infrared being slightly longer cuts through, and you can see there's something interesting structure in the middle. Now, if we look at it in X-ray, we have a completely, you don't even know you're looking at the same galaxy, but actually this is the same orientation, right? It's a different probe, but they've angled the picture so it's the same. And that circle that we could see in infrared, you can see this enormous jet coming out of it this way, and then there's another one going back over here. So this is a quasar. What we're looking at here is a quasar. There's a supermassive black hole in the middle of this galaxy that is not apparent to us at all in visible light. And then there's a hint of it here. That's the accretion disk going around a black hole there that's giving off a lot of infrared light. And then that accretion disk is creating these jets, these super energetic jets, right? Which then if they were pointed at us, we would see as blazar or quasar. And so this is a really good set of images that I really like that shows the power of going outside the visible range in astronomy. Okay, that's a good stopping point for today. We'll talk more about this later. Thanks for listening.